or
starting. Yeah. So good afternoon, ladies and gentlemen. Here's Yaolin Wang from University of Liverpool. So today it's my honor to give this talk. I will mainly introduce my work on the plasma processing of naphthalines for industry problems. So here's the main contents today. I will quickly go through the background, which I have told before. So about the pH caused industrial problem. And my work have two stages. The first, I will briefly introduce my pre-experimental work on naphthalene decomposition, and then I will focus on the development of a basic hybrid machine learning model to predict the precise performance based on the limited experimental data set. So let's talk about the biomass. It is considered to be one of the most potential renewable energy source without zero net emission of carbon dioxide. The researchers have been developing serious technologies for biomass utilization. So among those technologies, the gasification is regarded as the promising ways to convert bioenergy into fuels, such as the carbon monoxide, hydrogens, or methane. So basically, the whole gasification process includes drying, pyrolysis, oxidations, and reductions. And during this process, a series of bar and coke will be produced, and the pH is one of the major components of the tar. So when tar is produced in the gasification process, it will reduce the efficiency of the whole process and also block the pipelines or affect the operation of its equipment and also cause many serious pollution problems. So the main purpose of our research is to effectively convert these pHs molecules by using the plasma technology. So here's the gliding arc reactors we use in the reactions. And this video is taken during our experiments. And the purple arc is in the video is mainly due to the use of nitrogen plasma as because the nitrogen as the carrier gas, of course. And also when we use the ICCDs to detect it, we can observe the discharge between two electrodes, and we have found only one arc. It happens between two electrodes once a time, but the time scale is very limited. And also based on our experimental plasma system, the discharge power is between, we use this between the 40 to 100 volt, and initial naphthalene's concentration is controlled by a warm water bath. And all the products and byproducts are analyzed by the GC and the GC mass analysis. And here are the experimental results, which I have reported before in Nijmegen. So as we can see that the different discharge power, naphthalene's concentrations, and also the different steam to carbon ratios, these three processing parameters can lead to different naphthalene's conversion, and also the product selectivity and the corresponding energy efficiency at the same time. So at the end of the first experimental stage, we proposed the possible reaction pathways of naphthalenes in plasma field based on the byproducts analysis and also the optical emission spectroscopy in the process of steam reforming. And here is the proposed reaction pathways. So next, due to the above experimental research on the plasma reforming of naphthalenes, so we found there are many reaction parameters and cannot be continuously changed in the practical experiments. So we so at the same time, and also when we do the experiments, the time is quite long for each point. So it's very difficult to carry out a large experimental data set to optimize the part of the reaction process. So I tried hybrid machine learning models based on the ANN, SVR, and DT. These three are the very basic and classical algorithm to deal with this ultra small data set. This data set, all the data is from the experiments. And also all the models are developed using the scikit-learn library in Python. So we use this hybrid model to analyze the regression problem of these three inputs and also three outputs out of the experimental data sets. and predict the selective 3 target indicators, these 3 outputs, and further to comprehensively optimize the reaction process by analyze the synergistic effect between these 3 input processing parameters. And then we defined the optimal things is the global desirable functions. Here we just introduced 2 9-dimensional index. So in this page, I will introduce the logical structures for the prediction and evaluations using this hybrid model. So first, according to our, because of our experimental data is very limited, so we use the discharge power, initial concentration, and steam to carbon ratio as the 3 input sites and put all of them. Why we choose these 3? Because in our experiments, we have proved that these 3 parameters have strong correlation with the reaction performance. So then go into the hybrid model, which mainly composed by the AN, SVR, and DT. The whole function is plots like this with different weights. So there are many hyperparameters in each algorithm. So we need to use the genetic algorithm to optimize and determine these hyperparameters in this model. And then the output side is the conversion and carbon balance and energy efficiency in this work, because they are the key performance indicators we know as the KPIs in the industrial process in the practical environment. So then I will briefly talk about the optimization of hyperparameters using the genetic algorithm. So totally we have 4 it has been listed in this table. We have 4 hyperparameters, and here we take one of the parameters is C in the SVR model, for example. So this is a simple logic diagram of the genetic algorithm code for the parameter C. So first, we randomly generate 200 values of C in the range of 0 to 2000 in this range, and those seeing this as the first populations, and then use this volume of Cs in the SVR models and do the prediction and get the result and calculate the mean square error, we know as MSE. And the code does the crossover and mutation operations to obtain the next generation, and then get a new value of C, and then repeat to the 3rd step for the loop. So in this work, I just set the number of iterations to the 200. So it's already high enough for this case. And through the genetic algorithm, so all these 4 hyperparameters of 3 algorithm can be determined and listed in this table. And finally, a final optimal value is use this. So we use this optimal value to build up our hybrid model. So then we also need to determine the weights for 3 algorithms. So we just label it W1, W2, and W3. And the weights of these different algorithms are optimized using the exhaustion method to let the mean square error of this regression problem reach the lowest point. So here is the median point. So at this point, it means the prediction is very accurate than any others points. So in this point, we confirmed our optimal hybrid model. So the final optimal hybrid model is in like these functions. And also from these figures, on the other hand, we can also compare the MSE in these 3 red circles. That means just we can compare 3 single algorithm we used. And from the results, we can find the decision tree, the DT's model is more suitable than other two because they have a lower MSE value. So based on that optimized hybrid models, we can see the predict output. So all the above two figures that effect of different initial considered discharge power on the Naphthalene conversion. So the three following figures study the effect of the steam to carbon ratios and to the conversion, carbon balance, and also the efficiencies, the three KPIs. So we can compare by comparing the predict value with the real experimental results. It can find that the predict value is in a good agreement with the trend of the experimental value. That shows that the prediction result of this hybrid model has a certain reliability. Yeah, and then we also need to validate our hybrid model. So we randomly selected 20% of the data points for the prediction and made a regression analysis with the corresponding experimental value. And these three figures show that the consistency of the model is very good. So the R-square is above 0.997. And this can be used for the validation of our optimized hybrid model. So in addition, we also analyzed the relative importance for these three input processing parameters. And we can find that when we consider this conversion, so the steam to carbon ratio has a 48%. It shows that the conversion is more easily affected by the steam to carbon ratio. And for the energy efficiency, it's much more easily affected by the discharge power. And for the carbon balance, will be mainly determined by both the steam to carbon ratio and also the discharge power parameters. So finally, we can use that predict result to do more synergistic effect prediction. So we use this hybrid model to predict the three-body interaction of the whole process under different operating parameters. So we plot like this. And the above three figures, these three figures is correspond to the conversion rate, carbon balance, and energy efficiency when these three processing parameters changed. And additionally, we can carry out more comprehensive optimization analysis. So we introduce, as I said, introduce dimensional index known as the global desirable functions. And the first one, the I1, is investigate the overall reaction performance and considering the both naphthalene conversions and the product activity at the same time. And on the other hand, the I2, we take the energy efficiency into the I1. So we get a much more comprehensive analysis. So in this way, we can see that in the following these two figures, that the red color is the optimized area based on the hybrid model. And we can also see that the right distribution of the I1 and the I2 is different. That means when we considering different optimal objectives, we can get the best operating conditions respectively. So based on the prediction results. So here's the summaries. We use the gliding arc plasma to study the decomposition and steam reforming of naphthalenes for the biomass utilization in a practical industrial scale. And the first stage is we investigate the effects of different processing parameters on the conversion, product activity, and energy efficiencies. And also we propose the possible reaction pathways. In the second stage, a hybrid machine learning model has been developed to predict and evaluate the plasma reforming process. So finally, thank you for the support for the EUROPAH and also the and the help from my groupmates. So thank you for your attention. I think that's all.